Hello and welcome to our discussion on common drain amplifiers. We're continuing from where we left off last time. We derived the gain equation to be GM times RS over 1 plus GM plus GMB times RS. So this is the gain equation we derived last time. Let me put that in a nice box here. Okay, and let us draw the circuit. Not being very creative in my choice of colors today, but yeah, whatever works. So I'm sure we understand the meaning of this. This is a common drain amplifier, and yes, so let's go ahead and draw the small signal model for this circuit. So we start with the gate as usual. I hope you've watched the small signal models lecture I think it's in the MOSFETs playlist of our channel, and it's pretty interesting and it gets you started on this one. So let's call this V1, and this is the source to which we have a RS connected. This is the V out going from there. And here we have a current source driving GM times V1 amount of current, and here another GMB VBS amount of current. We're considering GMB. We generally don't do that, but now we're considering because we have GMB in the gain equation itself. So yeah, we better not ignore that. Alright, so pretty simple, isn't it? So from here, let's derive the gain equation. Okay, first of all, V in, look at this, it's going from the ground to this point to where V1 starts, right? So V in equals V1 plus V out, right? V out is this much, so V out, right, till ground, top to ground, that's all. V1 plus V out, right? Let me take a different color, this is too dark. So this is equation 1, and so we'll have to keep coming here. What is the second equation? If you look at VBS, right, the bulk to source voltage, first of all, let's see where that is here. So this is the bulk, right? It's connected to the ground, and so the bulk to source voltage, VBS, can be given by VB minus VS, right? Okay, so VS here, the source, is the V output, right? And VB is ground, so ground is 0 minus V out. Therefore, VBS equals negative V out, right? Okay, let's put that here as the second equation. VBS equals negative V out. It's the second equation. Alright, now from here, let's write the equation for current, can we? So here's one current, here's another, and they both add up to come here, right, through here. So if we want to write those currents, this is GMV1 is the current here, GMBVBS is the current here, and here the current should be V out over RS, right? So we can have GMV1 plus GMBVBS equals V out over RS. It would be great if you're writing along with me so that you're not missing out, because I keep going up to the diagram, and if you have it handy, it'll be really helpful. Okay, so let's go ahead and substitute negative V out for VBS, shall we? So GM V1 minus GMB V out equals V out over RS. All it is now is just manipulation of the equations, substituting this and that for various terms and just, rearranging them. That's all it is. So for V1, what can we write? Oops, yeah. V1 is V in minus V out, right? So let's just put that there. V in minus V out minus GMB V out equals V out over Rs. So if we take all the V out terms to that side, we're left with GM V in equals V out, and I'm factoring V out outside. Or, let's do that again later. So let's just write this down first. V out GM from here plus GMB V out plus V out over Rs, right? So if we can factor V out out, we get GM plus GMB plus 1 over Rs, and here we have GM times V in, right? Alrighty, so just rearranging and taking the LCM here, not a big deal at all. So V out is Rs times GM plus GMB plus 1 over Rs, right? And here we have GM V in as usual. So if we can take V in under V out and put it on the left hand side, we get V out over V in equals GM times Rs over 1 plus GM plus GMB times Rs. That's it. Got the equation for the gain from the small signal model. Alright, no big deal. Let me just review what we just did here. All we did for the small signal model was first wrote what Vin stands for. I mean, Vin is equal to V1 plus V out, and the second was VBS equals minus V out. And right, we did this derivation here, right? VB is 0, VS is V out, so minus V out. Perfect. And then what was the third equation, the most important one? We added the currents coming from here to here, right? GMV1 plus GMBVBS equals V out over Rs, right? That's all it is, not a big deal at all. And then we just substituted stuff and rearranged terms and finally got the answer. Okay, all right. Well, let's. I'm sure I've done this in the last lecture, but just to recap again, if we have to plot the gain versus the input voltage, this is just 1, and let's look at this equation here real quick. I think I did this in the last lesson, but suppose Rs is really huge, right, nearing infinity or something. We can ignore 1 because we have an Rs here, right? So all you're left with here is GM Rs over GM plus GMB times Rs, and Rs can go. What you're left with is GM over GM plus GMB, and then finally, if you can factor GM out as well, what you're left with is 1 plus eta, right? So GM cancel. So 1 over 1 plus eta is the gain you can get, right? So AV equals 1 over 1 plus eta. And generally, eta is, you gotta extend this a little further. So generally, eta is 0.2 or slightly larger than that. So you'll have 1 over 1.2, so it's never 1, right? So your gain can be written as something like this. It doesn't go down there, it kind of gets constant. So 1 over 1 plus eta, right? So that's all it is, not a big deal at all. And I wanted to show you that. And one more thing I wanted to talk to you about. Oh yeah, so let me take a different color. So this is our common drain amplifier, right? So slight changes in V in are going to bring in large changes in the current in the circuit, right? For example, we know the current equation is given by half mu n C ox W over L V in minus V out minus VTH the whole square, and this is VGS, right? V in minus V out, VG minus VS. So small changes in Vn are going to bring large changes in the current because this is a squared term, right? So we remove the resistor from here because of nonlinearity concerns, and we replace that with another MOSFET, right? Just because it brings in a lot of nonlinearity if you use this, and also from our so many discussions before, we know that using a discrete resistor is not going to help you when you're doing integrated circuits. So that's all it is. This is just a V bias to a new MOSFET, and we can have a PMOS or an NMOS here. It doesn't matter. I mean, we'll look at those different applications later, but for now, just that it'll be a MOSFET than just a discrete resistance. All right, perfect. We will continue in the next lecture. Thanks.